So far in Chapter 8, we've talked about parabolas in 8.1, ellipses 8.2, and hyperbolas in 8.3. One interesting thing as we get into application questions is that for a parabola, if parallel lines come into a parabola and ricochet off the side, they will all go to a focal point. This could be for, say, a satellite dish. It could also be from a flashlight, in which case the light would come from the focal point and go out in parallel rays, and that's why a flashlight has like a beam of light. For a ellipse, rays coming from one focal point would bounce and go to the other focal point. So these rays would not be parallel like these here. That would be good for something like a lithotripter, which is a thing in the hospital where if you have an elliptical room and you send out a sound signal from one focal point, it could bounce in such a way that it could break up a gallstone that is inside of you that you wouldn't need surgery to do it. Also, maybe you know in the Capitol building down in D.C., they have a whisper room. So if people are standing at one focal point and they speak, somebody standing at the other focal point could hear every single reverberation of their sound. So it'd be good for like spying on foreign countries who are talking about things. For hyperbola, if the rays come out at one focal point, they don't go parallel like the parabola. They go in all different angles. This is great for headlights of a car, so you can see a very wide part of the road, as opposed to a parabola, in which case you'd blind the driver coming at you. Here's an application question for parabolas. If you have a satellite dish that's 4 feet across and at the same time it's 1.5 feet deep, and you are having parallel rays coming in from the for your satellite dish, and you want them to all bounce and go to your focus point so you'll get the best reception possible, where should the focus point be located? If we put the x and y axis in such a way that it hits right at the vertex of the parabola, and then we can locate this point, which would be the point 2, 1.5. And remembering the standard form of a parabola, what's upward opening, so x squared equals 4py. Then we could sub in our point for x and y, and we could solve for p. And p would be the distance that we would need to go from the vertex to the focus. So 2/3 of a foot up from the vertex point is where we should locate the microphone to collect the sound from the satellite dish. Here's an application question from 8.2. And we have a lithotripter right here. In the hospital, this would be a circular pool of water. The patient would sit on a chair, and then some kind of sound waves would be emitted from one focus point, and they would bounce off and break up some kind of stone that would be in the patient sitting in the bath over here. If the room or the bath is 10 feet major axis, that would be 2A, and 6 feet minor axis, that would be 2B. And remembering our Pythagorean identity for ellipses, where should the chair be located? Plugging in our numbers for A and for B, we can solve for C, and C would be 4 feet. So from the center to the chair should be 4 feet, or coming from the wall, it should be 1 foot from the wall. An application question for hyperbolas. So here's a comet that is slinging around the sun into and out of our solar system. And perihelion, the closest it gets to the sun, is 130 gigameters. A gigameter is 10 to the 9th meters. And when the comet is at one end of the focal width, perpendicular to the focal axis, it will be 390 gigameters. We have a theoretical center point out in the middle of space, and for this problem, we can set up a system of equations. C minus A, so C would be out to the focus point, A would be to the vertex point, so C minus A would be our 130 gigameters. We could solve for C. Also, maybe you recall that the distance from the focus point up to the curve is b squared over a. And so that would be our 390 gigameters, so I'll have to fix that. And b squared is equal to c squared minus a squared for hyperbola, so it's the regular Pythagorean formula. Our second equation can now be solved for a, because we can make the replacement and FOIL and cross cancel and get an answer for a. We could plug that answer in up here to get our answer for c. And we could use our Pythagorean formula to get our answer for b. And then we could write the equation for this comet in the solar system. So assuming that we're looking at this picture in this two-dimensional way here, orientation, and that it's opening in the x direction, then I would leave my equation with the x part first, and over a squared, minus the y part second over b squared. Some formulas to remember. Eccentricity is equal to the ratio of c over a. Now that only really makes sense for an ellipse and a hyperbola that have a distance c, center to the focus, and a from the center to the vertex, because the parabola really doesn't have a center. But eccentricity for a parabola always equals 1. Eccentricity for an ellipse will be a fraction, a positive fraction. If it actually equals 0, it's a circle. And eccentricity will be greater than 1 for hyperbola. In any case, though, including the parabola, it's the ratio of the distances focus to point on the curve and point to directrix. That will always get you these same answers. If we have this picture right here, which we have something that is could be a parabola, could be a portion of an ellipse, or could be a portion of a hyperbola. And if this vertex point is at 0, 0, and the directrix is here, then a random point that would be, well, not random point, actually, on the end of the focal width can be found. For a parabola, we would have the distance p and the distance 2p from 0, 0. From the ellipse, now the center is going to be over here somewhere, so this x value will be a minus c, and the distance up will be b squared over a. For a hyperbola, of course, the center point is going to be over here somewhere, so this distance right here will now be c minus a, but it will be the same distance up to the end of the focal width. So notice that in an ellipse, the distance to the directrix is further than the distance to the focus point, directrix, focus. But for a hyperbola, notice that the distance to the focus is longer than the distance to the directrix. So that's why these will shift direction when you subtract them for those two. Directrix can also be the distance from the center point to the directrix can be written in terms of a and c, a squared over c, and that would be only for the ellipse and the hyperbola that actually have a center point and that you can actually talk about the distance d.